Hello, good morning, good afternoon, good evening. Welcome to the webinar on the future of fusion material data, introducing the MatDB4Fusion project. We will start the webinar in a couple of minutes to give you room to be connected, to have access to all the information. So let's wait a couple of extra minutes. Let's see how people are connecting. So still one more minute to start. So I think we have given a couple of minutes. We have a quite packed agenda. So I would suggest we start it again. Good morning, good afternoon, good evening, everyone connecting to this webinar. Thanks for being there. We are going to introduce the project, introduce and present the project of the Future Fusion Material Database. It's a project that has been already pre-presented in a couple of conferences, and we want to provide you the whole information to show you why international experts are supporting us, which are the added value of having that project available to the community, and give also you the room to ask whatever you feel you like. For asking questions, please type in the chat. We will have a Q&A session at the end of the webinar, so feel free, and after the webinar you can also contact us. Just for your information, the webinar is going to be recorded and it will be available for those who want to visit and check whatever element, how the database is working, and again to contact us for further questions. So, said that, we are going to start with a brief introduction to our speakers. Next slide, please. So, as I said before, we have a number of international experts who will present why the database is relevant for them, for their work, why they joined this international working group, and which are the capabilities of this new tool in the community for the particular projects. So we'll have Dr. Jim Pickles from Tokamak Energy, Dr. Greg Sinclair from the D3D, Professor Arun Pachatara from University of Birmingham, and Dr. Julia Spranger, who will present how OCDNA is collaborating with this database, and which is the role in general of OCDNA data bank. After that, Dr. Philip Liet, who is the person leading this project at CATF, will make a full explanation of what the database is, how it operates, how to engage with us, which are the possibilities of engagement, and all the features that you can find today and what we want to do in the future. So next, please. The agenda of this webinar, we will have this brief introduction to CATF and the project, why this MatDB4Fusion matters, and we'll have the voice of external experts, the role of OCDNA, as I mentioned before, MatDB4Fusion in detail. We will have a demonstration of how the web application works, and finally, how to be part of the project. And we want to allocate at least 10 minutes for Q&A from the participants. Again, the agenda is quite packed. Let's try to be efficient. Next one, please. So the first thing, what is CATF? Why CATF is taking care of that project? Which is the role of CATF and why we have a fusion program? So CATF was founded in 1996, something around 25, 30 years ago. It's a non-profit organization. Headquarters are in Boston and Washington, and with an office also in Brussels. Our mission is to push the technology and policy change needed to achieve zero emission, high energy planet, and at affordable cost. And our vision is to meet the world rising energy demand in a way that's financially, socially, and environmentally sustainable. So, just to make it clear, headquarters are in Boston, but we have a global scope. We work in US, of course, we work in Europe, in UK, in some countries of Latin America, in Japan, and so. So the Fusion program is a global program, and within this mission and vision, 3 years ago, they were monitoring Fusion. Fusion is becoming a reality, and they decide, okay, we need to open a program on Fusion. And this is why the program on Fusion exists. I'm Sheila Gonzalez, I'm the director of the program, and one of the projects of that program that we feel we could help the community is this international material database. Next one, please. So, how this project was set up was a couple of years ago in a software conference. I have a number of people coming to me and say, we need to do something related to materials, to data for materials. Data is available, but it's dispersed. There are gaps. We cannot identify the gaps properly because there is not an integrated database. We cannot apply all the new tools related to machine learning, artificial intelligence, because we don't have this data group it and group it properly, and we need to do something. And they say, let's work together to put this database at the international level. And this was the origin of this project. We know it was going to be difficult. We know it was going to be challenging. We knew we were going to have a lot of discussion because data and collecting data has IP features, I wouldn't say issues, feature associated. But here we are after 1 year and a half or a little more of work, a lot of internal discussion, how to organize, how to set up some tool that is useful and at the same time people can feel comfortable putting data in that material database, and we got it. All the details of this database will be shown in detail in this webinar. This is why we are doing it, and I hope you take full advantage, and any feedback, any comment from your side is always very welcome. This the database is a result of an international working group. You will see how to join that and to how to participate in this conversation, that the result of the conversation is not just to talk, it's something that is real, is meaningful, and is this database. So I have mentioned the need of collecting data, the data available in the literature, but not put it in a proper way to be able to group them and being useful and to be able to apply these new tools which are now available. All these things will be explained by our guest here and part of this working group, so I will not go into details. Just I want to highlight that there was and there is an urgent demand for a global database for fusion material properties. If we want to increase the TRRs in materials for fusion, which is essential to have a fusion power plant, we need to have a meaningful, credible material database. And this is the whole spirit of that project. Please, next one. So we now move to the part of why MatDB for Fusion matters. And our first speaker is Dr. Jim Pickers from Tokamak Energy. So please, Jim, the floor is yours.
Great. Thank you very much. Yeah, I just like to focus on something you said there, which was the word urgent. And I hope I'll give you the reason why we're so excited to be part of this and so eager for it to happen and happen as quickly as possible. So if you go to the next slide, please. Yeah, so who we are. So we're a private fusion company. We're headquartered in Oxford, but we have a global reach, and our approach is very much to partner with people around the world. So we're sort of a medium size, I would say, fusion company. So there's a lot of people in our situation, a lot of fusion companies popping up all over the place of our sort of size and with our sort of needs. So I think what I'm saying here probably applies to a lot of companies out there. If you go to the next slide, please. So we have a specific fusion technology focus. We're looking at spherical tokamaks and we're using high temperature superconducting magnets. And those are our two sort of technology raison d'etre. And if you go to the next slide, we're involved, as I say, with global partnerships around the world and particularly looking at some of these public-private partnerships. At the moment, we're part of the US DOE milestone program. And coming back to that word urgent, third bullet down, the whole point of this DOE milestone program is to start operations by 2034. So that's not an awful lot of time. So the sort of challenges that we're looking at, we have specific concerns because of our technology choices, that we need a very good blanket with major material challenges there. The magnets, obviously, very high intensity plasma, so we need a very good first wall and a very good diverter technology. And then we need the very best neutron shield materials. So we're all talking all about state-of-the-art materials here, and pretty low TRL. And if you go to the next slide, this is the slide that keeps me awake at night. So this is showing for our first of a kind plant when we get to the point where we're uncertain about the data. So it's the big concern is the irradiation damage of the materials. And for four of our key materials, Rapham steel, vanadium V4 for tungsten and tungsten carbide, you can see those gray bars as we get to the radiation levels where there's not enough data there. There might be a few data points that we've got access to, but not nearly enough. And if you go to the next slide, that basically this is after a few years of operation, we enter this cloud of uncertainty. And if you go to the next slide, please. So the problem with this cloud of uncertainty is, and as I say, this is the private fusion company perspective, and being a private fusion company, it tends to give you a bit of a mercenary mindset. And we're all about the money. We're all about how can we make our offering and fusion in general an attractive investment. And if you look at it from the investment side of things, sorry, if you go back one slide, this cloud of uncertainty is unquantifiable at the moment, and investors hate this. They're okay with risk, as long as you can quantify that risk. So there's certainly going to be some uncertainties about it, but if we can quantify it, then the investors will still be happier in putting money into the various fusion projects. So if you go to the next slide, this is just to illustrate the incredible value of having good data. And this is something that I did just last week with the MatDB4Fusion data. And I should say, as Sahila pointed out, we very much had the AI capabilities in mind during the inception of the database and also in its design, everything that Philip's working on in shaping the design, it's to make it AI ready. So just as an example, if you go to ChatGPT and you put a suitable prompt and you just drop in the database information, it very quickly plops out a model. If you just say, I would like a model that would allow me to provide some quantification around the uncertainty for one of these materials, it'll give you an R squared value for the data. It'll then say what the important features are that are guiding that model. In this case, the test temperature and the gauge width. It'll give you a breakdown of the model. It'll give you a level of predictive power. It'll also say how to improve that model and get better R squared values. It'll give you the uncertainty. And it will then say feedback into the database to say, if you could add these features to it, we can improve the fidelity of that model. So it's a little bit glib here, but I'm saying as of 2025, the analysis is trivial. It's certainly got an awful lot easier, but we have to have the data. So just going to the last slide, we all need more data, and that's why we really, really need this activity here.
Thank you very much, Jim. This is a really good explanation why data is so important. So the next international speaker will be Greg. Please, Greg, the floor is yours.
Thank you, Dr. Gonzalez. Yeah, my name is Greg Sinclair. I'm a scientist at General Atomics, and today I'll be talking to you specifically about D3D, which is a tokamak in San Diego. Next slide, please. I don't think it's a surprise to many people in the audience how much of an immense challenge it is that in designing an inner reactor wall that is robust and resilient. These surfaces that face the plasma in a reactor will be exposed to extreme conditions. This is just a Venn diagram showing, the thermal loads, the plasma loads, and the neutron load on these surfaces. Incredibly intense, something that no one has ever designed for before. And to actually design these materials and figure out what materials will survive in this environment, it requires us to understand the synergies between these different sorts of loads on the material. And we feel at D3D that this MatDB4Fusion effort can help function as a centralized database to explore these synergies and link the material properties to the performance, and especially when it comes to using this large array of data for these machine learning tools that can provide some additional analysis. Next slide, please. For some context, in case you aren't familiar, the D3D tokamak is the largest tokamak in the United States. This is a U.S. Department of Energy funded facility that exists in San Diego. General Atomics is the host of this facility. And at D3D, we have what's called the Diverter Material Evaluation Station. This is a removable sample probe located in the lower diverter. You can see here in the yellow circle here. And this allows us to expose coupon scale samples to fusion relevant conditions. You can see in the middle part of the slide how many different sorts of samples we've exposed just within the last 2 years. All sorts of metals, ceramics, even liquid metals to these conditions. And we have world-leading diagnostics that allow us to characterize various properties of these materials during loading. And this system has been working very well for the facility, and we have over 30 years of testing data now. Next slide. So the effort right now here at D3D is we've started working with the MatDB4Fusion effort, and we feel like this is an incredible place for us to invest our resources and to come together to centralize the sort of data. Um, Taking all of the experience that we have at D3D and all of the testing that we've done, exposing these materials to fusion relevant particle and heat loads, that has been populated by all these users, people coming to D3D to do testing, being D3D being used facility, having that data that they've been able to gather, but then actually synthesizing that data and putting it into a database where it can be centralized, and then gotten from one location to support not only other publicly funded entities, but the industrial fusion effort that's being ramped up very rapidly right now. We have incredible valuable data as you see here on the slide: erosion, thermal response, surface evolution, and these sorts of synergistic effects are really hard to find in other facilities. And so we feel like D3D can contribute to this effort in a meaningful way. And as it says on the slide here, we really want to actively support this effort. We've already invested resources here at the D3D facility to make this, to integrate this data into the database and make this data accessible to the larger fusion community. And not only the database will have this information on the material properties of the as fabricated material, but then also how this material will perform under these fusion relevant loads. I think that's all I have. I can go to the next slide here. And I just have a website if you wanted to learn more about D3D. But yeah, we're actively involved, and we look forward to hopefully engaging with you in the future. So
Sorry. Thanks a lot, Greg. And I like the point that you highlighted about using the database to transfer that knowledge. That in particular, you as a public institution has there, and you have to find a way how to transfer that knowledge and this information to the whole community. And this is one of the key elements of this database to be able to be used as this vehicle to transfer the knowledge. So next speaker is Arun, please. The floor is yours.
Hi, thanks, Sahila. So I wanted to make a slide, but then the work became so much that I just couldn't do it on time. So my apologies for it. So I'll probably just go on a monologue. So yeah, University of Birmingham and certainly from my group, we have been involved with this work since its inception when this was started. So for other people who are listening, just to highlight, we are the largest fusion materials and nuclear materials group among any university in Europe. We will be 21 people this year, all looking at different aspects of materials. And one of the pledges that we do have from our group is whatever data we will produce, all of them are experimental data ranging from manufacturing to irradiation testing to plasma wall interaction effects. We will be making that available to the MatDB4Fusion as much as possible. And I would say 90% of the work that we are doing would be relevant for what we are doing enhancing the data quality and enhancing just the database available. And I think this is really important as Fusion moves from being a fundamental science project to an engineering issue, because we do have very complex environmental damage scenarios that are expected in fusion devices. And historically, national labs and universities across the world has been producing tremendous amount of data. So compilation of that at one standardized, secure manner, which can guide worldwide fusion efforts, it is the right thing to do. So we are very happy to be part of this, and we will continue to support as much as we can throughout the initiatives here. Um, there is, as the slide says, there is about four decades worth of data that has been compiled. I would argue it's even longer than that for certain specific areas. And one has to have confidence in designing the first of a kind power plant. The way you get that confidence is you have confidence in the data that has been added somewhere. So MatDB4Fusion is doing exactly that. And I think we must sort of understand that data quality matters and storing a data at a specific location matters. And even if certain data points do not fit within the data quality regime, we shouldn't be throwing it away. We should be storing it somewhere, because with the advent of AI technologies, suddenly those data quality that we may deem today not valid may certainly become valid. Data is much more in today's world, data is much more important, and there is a lot of value being put there. So I really appreciate the effort that we are putting towards as an international community. And congratulations actually to Sahila and Jim to taking this on board when this actually started and getting it from where it was to now through hard work of Philippe, weekly meetings on getting it at a platform where people can now start using it. So this is an incredible thing. From our side, we do, as I said, we have lots of programs we are partnered with. We have partnered with even Tokamak Energy on shielding issues. And I think as much as possible, we would be making that data openly accessible. Of course, protecting some of the things that may be trade secrets, but anything that is openly available, we would make sure that that goes into this database so that other people and people in the community, certainly in the Western world, can use it.
You very much. I will highlight what you have mentioned, and Philip is the one mastering all this together with the international working group, of course, is this categorization of data, which is really time consuming but very needed. Compilation of all the data available in the literature is a huge task, and this is something that at the end of this presentation we'll see this request for help for the community. It cannot be done by a single entity or even for a number of individuals. You really need a lot of work, but we can all contribute to that and to storage all available data in an organized manner that could benefit to the whole community. And this is something, just this categorization and storage of the data is a huge added value. On top of that, all new data coming, as you mentioned, Jim mentioned, and Greg, all this new data coming and populating the database. It's a huge effort. It's an effort that belongs to the community, and this is why we are really proud of have already big part of the community involved, and now newcomers we expect to join the project now that they can see and they can understand more in detail what is the whole purpose. So with that, I will give the floor to a Second, I mean, I would say a big part of that project, something that we wanted to, where we wanted to host the database. This is a huge effort. We didn't want this effort to be lost in any case. So we say, okay, we need to find some international organization that provide confidence that no matter what, the database will remain. And that was OECD, the bank, the data bank. We found it there, the, the infrastructure that we needed to be sure that all this effort, no matter what, will remain and will belong to the community. CATF is leading, and we are very proud and we'll push for that. But every single user, every single contributor should know that is in an international organization database in the data bank, and the database will remain there forever. So, Julia, please, the floor is yours.
Thank you for that introduction. My name is Julia Sprenger. I'm a data engineer at the NEA Data Bank. And for those who might have heard about the NEA but are not sure yet, I will just go a bit through the history and what the data bank, the NEA actually is doing. So the Nuclear Energy Agency has quite a long history. It was founded in 1958 as a forum for cooperation for the most advanced countries in the world. So it is based on a number of member countries, and today this counts to 34 member countries as being part of the Nuclear Energy Agency. The two main missions of the NEA are to assist its member countries in maintaining and further developing through international cooperation the scientific, technological, and legal basis required for safe, environmentally sound, and economical use of nuclear energy for peaceful purposes. And furthermore, as a second mission, to provide authoritative assessment and to forge common understandings on key issues as input to government decisions on nuclear energy policy, and to broader OECD policy analysis in areas such as energy and the sustainable development of low carbon economics. So the NEA is operating under the umbrella of the OECD. If you move to the next slide, please. The NEA is overseen by a steering committee and a diverse number of technical committees, which are overseeing the work of the NEA. And the work is actually organized in about 72 working parties and expert groups, gathering experts from diverse countries and organizations, as well as 18 international joint projects. Next slide, please. And the number of projects hosted and coordinated at the NEA is quite a large number. Here I'm just giving you two examples of fusion-related projects that are currently taking place or are being hosted at the NEA. One is the Shielding Integral Benchmark Archive Database, short SINPAD, which contains data of 105 reactor fusion, neutronics, and accelerator shielding experiments. And the second one is the Joint Evaluated Fission and Fusion Library, which is quite a large project, having 2 meetings per year during the Nuclear Data Week, which is actually happening right now, and also has quite a large, a part that deals only with fusion topics. And I think in this company, the upcoming MatDB4Fusion project will be quite well kept, and I think it will be a nice addition to all of the database projects which exist already out there and are distributed by the NEA. Thank you.
Thank you very much, Julia. I have to say the decision to go to CDNA was not done without a really big internal discussion within the working group, analyzing a number of options, finding pros and cons of each one, and we end up being there, and I think it was really the right decision, as Julia have shown this transparency, this accessibility of data, and the variety of projects that you have already hosting. So that provides some guarantee to our database, that all the efforts will be there, storage, and available for the community in any case. So now that we have seen all these comments and you have a better understanding on why and how and where we are hosting, we go to the important thing, the database. So Philippe, who is the one leading that project within CATF, will show the material database in detail and will provide a demo to see how it operates. So please, Philippe, the floor is yours.
Yeah, thank you very much, Sahila. Excuse me. So, as you probably heard already, I'm the MatDB4Fusion project leader, and I'm really keen to show you here what we built since the start of the project last year in the following slides. And the speakers before made pretty clear there's a huge demand for Fusion material properties data already, and due to this demand, just to give you some historical background, the International Working Group formed end of 2023 with the aim to create a global database, which we call the Materials Database for Fusion, or MatDB4Fusion. And this has the aim to bring everything together, all kinds of Fusion material data. And there are many stakeholders here involved from private companies, from US and from Europe, also many large public entities like Eurofusion, for example. And it was thought to have a neutral international leadership, therefore Clean Air Task Force, which also fully committed to fusion in exactly that year, was willing to lead the efforts, as already mentioned. So the ultimate vision for us for the database was that it should cover all kinds of materials, properties, but also supporting data, which and by which we mean also like experimental raw data, which are relevant to fusion design. And it should be an international database, independent of local governmental decisions. Additionally, there should be some quality control implemented, for example, tags by which we can discriminate data by certain quality criteria, like indicating that specific standards are used for the experiments, or how to or how complete the data set is. And then besides open access data, there should be also restricted data sets included, where intellectual property rights might be of concern. Overall, it should then act as a single reference for fusion reactor design, and it should help to access data which are not accessible in the public, for example, reports which are staying in repositories for many decades. And it then helps also to assess data gaps and reduce the application of effort. There we clearly need to think of very expensive irradiation campaigns with a duration in a scale of many years, where a clear focus on the most crucial, the most needed experiments is crucial. So it should also accelerate the creation of codes and standards. Their data quality is of highest concern, but also provide sufficient data for machine learning solutions where data quantity is also needed. And as I said, the development started then in 2024, and we reached many milestones since then. For example, the database schema and the database system is running. Also the API and the web app now currently launched. And we have now reached a status where we say we can release the database and enter in a new stage where we seek close collaboration with the community, with you. So metaphorically speaking, the seed is planted, and now we can watch the tree can grow. So next up, I'd like to show you a bit more details about the database content and its structure. When we talk about a materials database, this is very abstract, and while we collected feedback, we have been confronted by many different ideas. The central question is also what are the smallest bits or grains from which the database could be built up. If we have a look at the literature, like here, this is metadata from Arun. there are many data points here and also average curves in order to understand and predict the material behavior. But the key point is that each data point here represents a single experiment. And so it should be a reasonable idea to take a single experiment also as a basis for a single entry in the database. But then the question is, what exactly is an experiment? This seems like a very simple question, but people can have very different things in mind. And we clearly have to stick to a properly defined schema. So when we have a look at the procedure of an experiment, for example, for a tensile test, then we can separate the whole procedure in different segments. And what we would have to begin with is some bulk material which can be made in a lab or by a commercial manufacturer. So there's a process which includes, for example, sintering, one or multiple thermomechanical treatments until you have bulk material. And from that, a specimen is cut with a certain geometry. This is sometimes irradiated, also sometimes heat treated again, until it is until with that specimen the experiment is conducted with certain specifications. And then you can measure, for example, the applied force versus displacement curve and interpret values for yield strength and ultimate tensile strength or elongation. So you have a material from which a specimen is made, and then the experiment is conducted. But there are multiple specimens can be made of this material, and sometimes even multiple experiments can be conducted. But there's always a one-to-one relation to the results of the experiments. And therefore, we take the experiment as the main reference. So each line contains another experiment linked to information of the used sample and the material. And then there are other information we can add, for example, regarding to publication, user information, data quality, evaluation, and so on. To give you an overview of the content, there are different materials to be represented in the database which are relevant for Fusion, and we clearly have to set here priorities. We decided to start first with tungsten, which is of most interest currently for the diverter, but also with steels. And these are then linked to preconditions containing manufacturing details or irradiation conditions for samples. And these then are linked to the properties, which are basically the experimental results from all kinds of measurements to acquire, for example, tensile strength or thermal conductivity. So still, this is simplified here, and we see here a snapshot from the normalized tables in the actual SQL database. And if you have a look here at the grand scheme, you can see that this can get really, really complicated. But besides this so-called analyzed data in tables, we also plan to include experimental raw data, like I mentioned before. And these can be linked then to the analyzed datasets above. This can contain, for example, EBSD data or stress strain curves. Then the question is, when we have a huge pile of experimental data, how can designers actually gain value from it? And there we want to offer some summarized data format with average curves and mean values in the so-called compendium. There we have to define calculation models to translate the analyzed data to the compendium. But overall, we are also taking here inspiration from the Fusion demo database with the so-called Material Properties Handbook, which already exists, which took also formally inspiration from the ITA database in the past. Now, speaking of machine learning, and what we think we can get out of it. There are many different use cases we could think of. Just to pick some, Knowledge extraction is a very interesting topic to gain data for the database itself. Also physics-informed models, anomaly identification, or uncertainty quantification for the component design. However, we should be aware that machine learning is also often used as a buzzword, and we have to thoroughly check for each case if it is worthwhile to be implemented, and most importantly, if it's reliable. But for us, there are here three major purposes we have the main focus on currently, which is the knowledge extraction clearly, but also the data analysis of the data inside of the database and a large language search function of the database content. Now, next up, I'd like to talk a bit about the database access models. We have here a concept in mind where we have first off a huge part of the database published as an open access data. So this will be provided and published under an open access license. And this will be available to all registered users with an NEA account. And the compendium will be also a huge part of it. So designers can make the most use out of this database. But then we plan to have here also restricted data sets. So for example, we have here data owner, which has data under intellectual property rights. And there we can define a custom license agreement for them. And with that, the data owner can then upload the data into a separated area of the database, a secured container, and then there are different constellations possible. For example, the data could be used to generate the compendium. So not the original data are shown, but average values will be generated together with the open access data. It could be also the case that data owners want to share data in between if they want to have a license agreement between each other. Or the data could be shared just within the own working group and that it's or the institution. So the database would be used as a kind of a data hub. And when later on the data is already available in the proper format for the database, they can decide if it's useful to compare the data with the available data of the database. So we think we came up here with a model which is very flexible for the needs of the data owners, and nearly everything is possible depending on the customized license agreement. Regarding also machine learning, the idea is here to export the data to be worked on in a secure, isolated software container. So ideally, the machine learning developers then provide the model to the container without direct access to the data. And then the training can occur, and the output is reviewed by the database administration, and feedback is given to the machine learning developers. But again, data owners can allow or reject the use of their data for the machine learning algorithms. So the message here is everything is optional. Then the question is how to contribute to the database. We have here three main ways you can go, or you will be able to go. First off, the experimental data can be put into a CSV template and with a specified format. So data can be imported into the database by uploading it to the website. Then a formal check is done in the background, and it is imported into the database system on a pre-major level. And it is also possible to use the NEA-hosted GitLab environment as a very granular and version control, and also then the validation checks are applied. But in the future, we plan to also include a website front end. On the website front end, some kind of form in which the user can put in the data as well. This will be the preferred way to contribute data when the system is implemented. And you can imagine it like a wizard-like user interface, which guides through the process of data contribution to make it easier. Finally, there's also the possibility to provide the data via an API request. So data can be fed directly to the database via automatic scripts. And therefore, if you think on a larger scale, data could be even delivered directly from a testing computer to the database. So the possibilities are there, and this is something we should have a look in the future as well. But for all provided data, the input is reviewed and evaluated before it is published by the database system. Regarding the queue and possibility to upload the CSV via the website, I'd like to directly jump into the website demonstration. So I'd like to showcase here the database web app we put together with a small demo data set. On the website here is currently implemented two of the most important aspects, the database explorer, but also the data contribution side, which I'd like to hear first up. And there you can download a CSV template on this button. And with this CSV template, you can enter your data in a specified format until you upload it again and send it to us. And then it goes through the formal check. Now, coming to the central part of the website, this is the Data Explorer, and we have here we are here first greeted by a blank screen. This is because we have here different filter systems implemented. So first off, you can search for a specified data set which you would like to view. And you see here now, as I selected, for example, tungsten data, the data is filled into the table. And then you can check, for example, on the with all these metadata included on the far right, you also see all kinds of results regarding tensile tests here, total allocation, area reduction, and so on. Going back to the left side, we also have an additional filter layer on top of that. And if we have a look here at the column header, there's this little icon you can click and then select another filter. For example, we can search for a specific author, like my dear colleague Simon, and then you can have his information, his data filtered out. And you can then select specific entries or even the whole data set and export it as a CSV file and use it just like you want. But this is not all. We also implemented here a plot menu, and we can open this up on the upper right side. We can drag it, make it a bit larger, and there we can do some funny things. For example, we can have a look at test temperature and plot it versus the tensile strengths. And then you see already some a scatter plot here, which is not so much of use yet, but we can group it by the material ID. And there you have a very nice distribution of the data, and you can export this image as a PNG or JPEG and use it for directly for a publication if you want. Then we could go on and ask, why do we even have this distribution here? Why there's a difference in the tungsten materials? And a material scientist knows that there could be a relation of the ultimate tensile strength to the degree of deformation. And so we could have a look, for example, at the thickness of the sample, which is indirectly related to the degree of deformation. And there you kind of see already some trend. And when we have a look at and we can group it also via thickness, excuse me, test temperature. And there you can confirm that there's a specific trend, and we can reduce the sample size, the size of the database content to just room temperature, reselect the data set, and then there you have the scatter plot again, just for the room temperature. And we implement here also some regression, which does not make too much sense here on the bottom part, but you can get just a feeling of the data trends. But with AI tools, this could also improve in the future drastically, and there are different fits could be suggested even then. I could go on and on, but you get the point, I think. Bringing the data together here brings us endless possibilities, and we can discover correlations which might not be obvious before. Then to give you additional information and close this demonstration, I'd like to recommend you the About section, where you can get some background information, also with the just implemented FAQ, and you can check this out. And lastly, you can go to our contact page here and subscribe to updates to stay in touch with us and get news about further developments. So then the final question is how to be part of the project. Delivering usability feedback for the web app I just showed you here would be already a great start. Also, you can contribute data, your own data or data from the literature, and you can apply as a data reviewer, because in the future we want to implement also a system where you can review the data directly on the web app within the data table and leave comments and suggestions. And you can support also the software development or even join the international working group and shape the future of MatDB4Fusion overall. And with that, I'd like to thank you for your attention, and I'm really curious about the questions you might have.
Thank you very much, Philippe. This is a huge amount of work, as you have seen, and of course, it's not maybe too appropriate that I say, but done in a very serious and systematic way. And of course, you are going to be the user, so you are the ones who has to judge. And please, as Philippe said, provide feedback. We have a few minutes for a few questions that I will select from the Q&A. We have a comment from our colleague Luigi Candido from Kyoto Fusionary, that he highlights the importance of having the database. They say this will not only consolidate those data we use for designing components, but also put the basis to create a probabilistic assessment of material properties, allowing to construct confidence also under that cloud that we have for high DPA damage. And he's talking about the possibility of using probabilistic approach. Okay, this is true when we have the database and we are able to apply all these tools, we will be able to create this probabilistic assessment. This is one of the added value, as he correctly pointed out, of this database. We have, I think, very important question. Which are the data that we are collecting? Let me answer that thing. We aim to have a very comprehensive database. We started with tungsten because it was like the most immediate thing. We plan to expand on structural material or on ferritic martensitic steel, but the aim of the database, with your help, and Greg have shown the thermal mechanical data and so on, so, is to be as comprehensive as possible. It should be a global integrated repository of data for fusion. So the more the better. Every category of data should be analyzed and structured in an adequate way. a lot of work, but this is the aim of that database, to be able to be as comprehensive as possible. I don't know if someone from the speakers wants to add something to this question of what kind of material are we going to include in the database. If not, we move to the next question, which is a very specific one and very important from Maria Ortiz from Fusion for Energy. Say thanks to us. And the question, have you considered including synthetic validated data generated through different data generation machine learning? Philippe, Jim, is someone wanted to answer that? Arun, Greg?
Yeah, I can make a start here. The thing is that I would put it more like the other way around. We are generating the data from the data set, and we are publishing it more like in the format of the compendium in the summarized format. But we would not implement such generated data directly into the database, and so it would be more a result of the available content in the database, and we would always rely on the available experiments.
Okay. Jean, do you want to add something?
No, only just to back up what Philip's saying there. I think we just have to be a little bit careful about separating the sort of the raw data from the synthetic data. But I mean, obviously, it's a brave new world here, and there's going to be a whole load of new techniques and new ways of dealing with these data. And we need to be open to all of these with the right sort of caution.
Yeah. No, I think this question is really important because it shows how all the potentialities of this database, the new data that you can generate, how this will be handled. That is all discussed in the international working group. So Maria, join the group and let's join to the discussion. That is the important question and challenging question that we decided within the group. With that, I think our hour is getting to the end. I would like to thank, first of all the participants, all the audience that have been here paying attention during the whole hour to this new project. We are really happy to have your feedback, your suggestions. Join the project. This is a project that has to be done by the community. We cannot do it alone. I always say that thing. All your feedback, help, data is very welcome. And I would like to thank, of course, all the guests, all the speakers that they are showing how the material database can help them and how now they are helping the material database to be set up. The help is really appreciated. And thanks to Philippe, who is leading this really interesting but time-consuming project, because if you want to do it properly, is a very tough project. And this is the way how we want to do it with all this international validation that for us is key. So thank you very much, and we keep in touch. Contact us. Thank you. Bye.